Hi everyone. In this video we are talking about the Cross-NAND SR Flip-Flop, and the circuit looks similar to the Cross-NOR. There are two gates, in this case NAND gates. We have inputs S and R, but they're actually going to go through inverters first. So we still have S and we still have R, and our outputs are still Q and Q bar, but now Q is here and Q bar is there. And then we still have feedback crossing over the gates there like this. Okay, so that's our circuit, and we want to draw the truth table. So we have two outputs, Q and Q bar, and we have two inputs, S and R. And this circuit is based on NAND gate behavior. So let's write a little note for ourselves here to remind ourselves how the NAND gate works. With inputs A, B, and output Y, 0, 0, 0, 1, 0, 1, 1. So NAND gate will only be 0 when both inputs are 1. Okay, so possible values for our truth table, I'm going to have 0, 0, 1, 0, 0, 1, 1, 1. And again, these, just like with the Cross-NOR, this is going to be a no change state. This is going to be a set state. This is going to be a reset state. And this is going to be an invalid, illegal, not used state, right? Now we're expecting to see the same outputs here. So actually, let's do them. We'll do them one at a time, and then we'll put them in the table. Let's look at the set state first, just like we did last time. So I'm looking at this set of inputs here. I'm going to have 1 and 0 for S and R. On the other side of the inverters, that's going to be 0 and 1. Now, notice with our NAND gate behavior, anytime an input is 0, the output is 1. So as a starting point, this top gate here, we know that output must be 1 because of the 0 input. And then that feeds back to the bottom gate with a 1, and that output is 0. So we get Q being 1, Q not being 0, which is exactly what we want for a set condition. So Q is set to 1. For the reset condition here, the inputs are S being 0 and R being 1. So let's take a look at that. We have S being 0, R being 1. And on the other side of the inverters, that's a 1 and a 0. Remember, anytime the input to a NAND is 0, that's going to drive a 1 at the output. That gets fed back to this input as a 1, making that output a 0. So we have the condition where Q has been what we call reset to 0, and Q bar is 1, which is the opposite of Q. Now, for the interesting case where both S and R are equal to 0, we're expecting no change. So that's this first case here. So 0, 0. On the other side of the inverters, that's going to be 1 and 1. Now, if we look at the truth table, here are the conditions where and one of the inputs is 1, and we can sort of split them in two like this and consider, okay, well, if the other input is a 1, the output will be 0. If the other input is a 0, the output will be 1. So the output is always going to be the opposite of whatever the other input was. But we don't actually know what the input is. So I'm just going to write this input as being Q, whatever it was. That's going to feed back to here as Q, and the output will be the opposite of Q, which is Q bar. That Q bar feeds back to here, and the opposite of Q bar is Q. So it makes sense per the diagram that Q should stay as Q bar. Sorry, Q should stay as Q, and Q bar should stay as Q bar. So they're staying as whatever they are. Let's see that again with some actual numbers in there. So zeros and ones. We'll try both cases so you can see that it's true. So for the case where Q was originally set, we have Q being 1 and Q bar being 0. Now, if that was our starting point, this 0 would feed back to here. And if any input to a NAND gate is 0, we know the output is 1. That 1 feeds back to here, causing a 0. And we can see that, yes, there's no change, right? Let's take a look at, well, what if the output had started in the reset state, which is 0 and 1, would that still be true? Well, this 1 would feed back to here, and a 1, 1 causes a 0 output, so no change. And the 0 would feed back to here, which would cause a 1 output, so no change. So we verified that no matter the starting position of Q, the 0, 0 condition of SR will lead to no change on the outputs. And that gives this circuit an ability to be like a holding circuit and hold whatever data it has, even when the inputs go to 0. And that's what makes a flip-flop useful, is that the inputs can go to 0, but the outputs will hold their value. Okay, so we've got that last condition to look at, where S and R are both 1, that invalid state. So let's take a look at that. If they're both 1, on the other side of the inverters, that's a 0. Now, any input being 0 to a NAND gate is actually going to cause a 1 on the output. So we have this invalid state. It's different than the cross-NOR invalid state, which was 2 zeros. In this case, it's 2 1s, but it's still invalid because it's the case where Q and Q bar are the same, and actually we want them to be the opposite of each other. So we call that an invalid state, and it's not used. Okay. And actually, I'll add to this video, I'll scroll up a little bit. Just in terms of symbology, the diagrams for an SR flip-flop, they're just shown as a square with S and R on this side as our inputs, and Q and Q bar on that side as our outputs. So when we're building circuits with SR flip-flops, that's how we're going to draw it. It could also be drawn so that both outputs are actually Q, but the bottom one is given a bubble to an inversion bubble to invert it. Let me draw that a little bit nicer, indicating that the output is inverted there. So over here, essentially that's Q and Q bar, but I'll be using this method of drawing the flip-flop.